When we design machines, we typically think of working out the sequence of operations first. We don't really focus on the times, but actually the dependencies between different events. And that's one of the differences between Motion in 2009 and 2010. In 2009, we relied on keyframes to position things and sequence things, which makes it difficult to work based on an event finishing. In 2010, we've got a great new capability called event-based simulation, which enables us to do a more realistic approach to designing our machines. Let's take a look at the feeding mechanism for the base plate. So here we have a feeding mechanism, and we've got this lifter, which raises up, picks up the base plate, and then it gets extended across, dropped, and then it returns back to continue the operation. Let's look at how we do that. So we have our existing keyframe interface, but then we just click on the event-based motion button to bring up our tabular interface to define the dependencies. So let's start by raising up the lifter. And we'll just start it at time 0 just to get things going. And what we do is we provide an action for a given task. So in this case we want to raise the lifter. And it's a servo motor, which means it's positional based. So we can specify a particular value, say 112.5 millimeters. That's how far it's going to move relative to its current position. We specify a time that should do that operation over, and then an interpolation method. Cycloidal just means it starts and finishes with 0 acceleration. Now, what we need to do is, once the lifter touches the plate, is detach it from the tray. So to do that, we're going to base it on a sensor that's going to detect when the lifter touches the plate. And when it does, then we're going to go and turn off the mate that is currently locking that to the tray. It's just that easy. And then after we've detached it, we'll attach it to the lifter. So straight away at that same time, it's going to change what it's attached to. So we'll do that straight after the second task. And then we'll just pick the mate, so lock it to the lifter, and we turn that one on. Once it's reached the top of the lifting process, we then extend the lifter. So again, we'll base that on the task, which is raise lifter. You don't have to do these in any particular order because it's conditional based. So I'll pick this and change the value, and it's got to go 765. Over 2 seconds again, and we'll do cycloidal. And then once it's there, we need to lower the lifter. So straight after this task 4, we'll get our raise lifter operation, and because it's relative, it's pretty straightforward. We just bring it down minus 112.5, and we'll do it over 2 seconds again. And then we need to detach from lifter. So when it detects that the base plate's touching the carousel, we have a sensor to monitor that. And that's just, oops, sorry, this one here. And I think I pressed the wrong one here. Should be entry RAM touches plate. There we go. When that's on, then we'll just detach that mate we activated, which is the plate lifter lock. And then straight after that task, attach to carousel. So you can see it's very operational based, which makes it very easy to work out the dependencies. And you'll see it's building up again, diagram on the right hand side there, which shows those dependencies. Alright, once it's finished lowering the lifter, we can then retract it. And again, this is where the descriptions do help you a bit to pick the appropriate task. So we just get our extend actuator and change it to return back minus 765 over 2 seconds. And this is optional, but we'll actually get it to end when that task is complete. And that should be all there is to it. So we just click on calculate. So we'll see the lifter comes up, detects contact, lifts it up, locked together, it moves it across, starts to lower it down, detects the contact, locks it to the carousel, and continues on with the operation. So very quickly we were able to get that working, but what's really powerful is the ability to do change. For example, I might say, well, I want to speed up the raise and lower times, but slow down the extend times. So just like that, you'll see my Gantt chart updates. It doesn't know about these sensor-based dependencies until we run it. But you'll see it will update that on the fly as it solves. So it detects the contact there now. Zips it across really quick. Lowers it down really quick. So see, it's a very flexible system to very quickly evaluate different ways of sequencing things and really get your cycle time optimized for your whole system. Incredibly powerful and very easy to do just one location. When we look at the full model, you'll see that it's a little bit more in-depth. This one I didn't use the lockmates, that was a beta 1 restriction, and I haven't updated this model yet. But most of the work there is locking and unlocking components as they move through the system. But event-based simulations really is incredibly powerful for machine designers to go through and do these things. Not only that, remember we've got full physics-based motion. So if we select any of these components, for example, we could pick the base plate here and say look at velocity, and we'll just do magnitude for the time being. We can check to see if we're violating any requirements. For example, we may be concerned that we exceed certain accelerations that our package can't contain, or again for loading on joints and everything else. But we can see here it's just over that initial period where it gets positioned. So as I said, event-based simulation is an incredibly powerful tool, and I think there's a lot of value there for machine designers.